Today we have a new member of EcoPro, Zhifei Yan, who got PhD from IMPA in Brazil with the Rob Morris. He's going to give the first talk in Korea, rainbow thing. Please.
Yeah, hello everyone. Today we're going to talk about something like a rainbow thing. So this is this is a joint work with a lot of people, basically IMPA group. Okay, I'm sorry. Okay, let's start with a warm-up question. So given two colors, okay, red, blue coloring on EKN. Can you find a monochromatic Hamilton cycle? Sorry.
No.
Why?
The one vertex.
One
Yeah. Like before, but
Yes.
So there is a very simple counterexample. This is one vertex. This is the remaining word, and it's connected with every other vertex with red edge. And in the other world, we only have blue edges. So definitely you cannot find a monochromatic Hamilton cycle. Correct. So based on this, Lehel acts the following conjecture. Okay, now you cannot find one monochromatic Hamilton cycle, but can you find two cycles? Both of them are monochromatic, and they partition the whole Kn. So that's the Lehel's conjecture. Conjecture given arbitrary two coloring on EKN. There exists C1, C2 belongs to Kn, V, C1 intersects with C2, is empty, and V, C1 union with C2 equal to VKN. There exists rainbow, Lehel. Okay, this is a very old conjecture actually. I guess it's like 1917 or something when Lehel visited Memphis and they asked the question with Pedro or some other people. But later.
What does it mean, rainbow cycle here?
A rainbow cycle, sorry. Rainbow cycle. A rainbow cycle means for each edge in the cycle, it has a distinct color with any edges inside itself. Sorry? Sorry, not rainbow. Monochromatic.
Monochromatic.
Oh, sorry. Okay, monochromatic. Okay, I mean, you just have two colors, right? Okay.
The above example doesn't have red cycle, right?
Well, then after this,
You need to extend the definition. Like we consider isolated vertex and also isolated edges. You can see like a cycle.
Oh, you consider isolated vertex as a cycle?
Yeah, we need to extend the definition of cycle a little bit.
I see.
Okay. Remember like, sorry, I don't remember, like 80s or sometimes. So the first approved by Luczak, Szemerédi, Luczak, Rödl, and Szemerédi in 80s. Lehel is correct for sufficiently large. And sorry, not 80. I think it's like 98 or something. Sorry, we need to check. Okay, and later this was improved by Adam in 2008. Is correct for smaller n, but n will still need to be sufficiently large. And later this conjecture was thoroughly solved by Berry and Thomas. in 2010 for ON. Okay, the story is over. So this is just a background question. Okay, so I will have this background. So today we will not talk about the Lehel conjecture. We consider about proper coloring background. So, question: given properly age colored Kn. There exists rainbow on a cycle. Properly colored, properly age colored, sorry. Proper age can. Can you always find a rainbow on a cycle?
No.
Why?
You can color with n-1 color.
Aha, yeah. So before we use the secret weapon, let's just consider the following simple construction. So let's just consider about K4. So you give two edges here, two blue edges here, and two red edges here. So in the graph, this is K4, right? So K4 means like if we want to find a rainbow cycle, which means we need at least 4 colors. But here actually we just have 3. Yeah, 3. So in general, actually, by the Within coloring, like other people, like we just said, by Within coloring, because the minimal degree of Kn is n-1, which means we can always find a proper coloring, proper age coloring, such that we just use n-1 distinct colors, which means you cannot find a rainbow in a cycle. And actually, yeah. So no.
I have a question. I mean, if we apply the Bayesian coloring, then the number of vertices should be an even number. And what about the odd number of vertices? Can still we cannot find the rainbow?
You cannot always find.
Always.
Yeah. Okay. So we also asked a similar question like Lehel asked. So instead of 1 rainbow cycle, can you find 2 rainbow cycles? So that's what we want to talk about today. We can always find two cycles. Okay, C1, C2, rainbow. VC1 intersect VC2, put empty, and for sufficient largesse. Okay. So, for this result, I think you may ask some questions. So the first question, like, we got 2 rainbow cycles, right? You want to ask, how many common colors do they have? Right? This is a very natural question. So actually, I will tell you, we proved the smaller cycle has a larger root n log n ages. So, which means the common colors is at most days. Yeah, because we basically, by our construction, we basically cannot control the common color at all. So it seems very interesting to conjecture. Can you give some better construction such that to control the common colors of the edges, and such that it has at most maybe constant colors, or just 1 colors. Okay, I will write. You read something? Conjecture for properly colored Kn, you can find two cycles, two rainbow cycles partition in Vkn with at most one common color. Yeah. Why one? Because still by Wissing, which means we just use MS1. There exists a procolor and use MS1 colors. So the best you can do is just that, at most one. Yeah. So this is just conjecture. I think the conjecture seems quite interesting because by this we will study the property of a proper okay, or something. Okay, so before we talk about the proof, I will show you some other results related to this, and we will use for our proof. So instead of two colors, another direction is for just a proper colored Kn. So how large of a rainbow cycle can you find in the graph? Okay, so this is a very famous conjecture given by Anderson, 1809. So for proper colored, properly colored Kn, you can find a rainbow cycle with at least n minus 2 edges. Yeah, this is a very famous conjecture, and a significant result of this conjecture to approach this conjecture was given by Alan Pogrovsky in 16, who proved theory along Pogrovsky 16. You can find the rainbow cycles. There exists a rainbow cycle with n minus large O into 3/4 edges. And later this result was improved by Balog and Mola. By 19. So with n minus large O root 10 log n edges. So as I say, actually, our proof, the size of a smaller cycle have basically the size with the basically the same size with this order. So you can imagine what we do. Actually, we construct an absorber based. We use the absorbing method to construct another rainbow cycle outside this cycle. Yeah, that's the idea of the proof. Any question up to now?
So if that theorem is improved, then your theorem also almost automatically improved or not?
So sorry?
So if they improve that big O term, then does your theorem also improve that small cycle has more smaller edges?
We can talk about proof. Actually, we use a absorbing method. So once you can improve this, we use our method. We can directly get about this, but with some log factor because we need to take unit bound. But anyway. Okay.
I have a question. Can you take the middle word a bit down? Down.
The other way, the other way.
This one. Okay.
The first conjecture here. So, I mean, does it make sense to ask for 3 rainbow cycles, but with disjoint color sets?
3 rainbow cycles with what?
But with no common color.
3 rainbow cycles with no common color. I mean, you can just leave one vertex outside as a special cycle. I mean, as a little. Sorry. Aha, yes, because you can leave one vertex outside and think it as a cycle.
Okay.
And let me see. Yeah, I don't know, sorry. But anyway, it's still conjecture. Yeah.
I was just wondering if it follows from it, but probably not.
Yeah, I don't know. Yeah, let's think about it later. Okay. Oh, okay. How long is 5?
Oh, don't worry. You started at 4:30, right? So you have plenty of time.
Oh, okay. Okay. So now let's talk about the proof. So as we see, our proof actually the idea is very simple. Is first we use Yoji's result to find a very big rainbow cycle first, and then we will construct a special absorber such that you can use the absorber to absorb all the remaining vertices, such that you can find the rainbow cycle in the absorbed structure. So that's the point. So the first thing, like, what should the absorber looks like? So now I'm drawing the absorber. So first, you have a lot of triangles. Okay, the numbers of triangles should be something like little n. And then you find a path. Connect all of them. Okay, and every edge in this structure has a distinct color. Okay, this is my absorber. Okay, it looks very simple, right? Okay, let me see. So we call the vertices on the top the teeth. Teeth vertices. Yeah, it looks like the teeth, right? So we call it A1, A2, to A top. And we also call the fifth vertices like B1, B2, and to B top. B tau plus 1. And how long is the path? I mean, below. So, like W1, W2, like W tau. So if you choose tau to be little 1, the size of the whole structure should be little 1. So before we talk about how to construct such a structure, I will show you how does the absorber works. Okay, before we absorb any vertices, we can already find a rainbow cycle in this structure, right? So it's very simple. We just start from B1 to A1 to B2 to A2, and like zigzag. Go back to B top plus 1, and then go back to B1. This is a rainbow cycle. Because I already claim all the edges have distinct colors in structure. Okay, now how does it work to observe one vertex? That's the first step. Okay, you choose one vertex outside. The point, like, before we observe one vertex, suppose the cycle the cycle should have 3 tau distinct edges. If we add one more vertex into the cycle, which means I need add one more edges, 2 more edges into the cycle, right? At least 2 edges. So actually, what we're doing, like, we will remove. Let me see. We will remove. Let's say. Actually, for arbitrary, you arbitrarily pick a vertex here, and you fix. Okay, you can choose 2 adjacent vertex. So we have space, so we can draw it like W prime, And suppose you can find the following age from 8 to 1 and to sum here and for this and also to sum triangle on the top. Okay, sorry. Let me see. Sorry, this is wrong. The concept. Okay. Sorry. Ignore this page. Can find this and you can find this. Then I claim you can find another new rainbow cycle inside the graph containing all the other vertices including x. Obviously we need the 4 new edges have distinct colors with any other edges as well. So how can we find a new cycle? So, as I just said, if we just add one vertex into a cycle, so we need to add 2 more edges. One more edges, because a cycle with n vertices has n edges. You add 1 more vertex, which means you need to add 1 more edge, right? So.
Did you add like one edge from x to w, and then no, one is from x to w something?
Sorry?
I mean, I'm trying to understand the picture. So
Okay.
Did you add an edge from x to all the way to the triangle, the top of the triangle, or
Yeah.
is it the length 2 pass, or?
Yeah, so we fix 2 vertex here, and we make this 2 edge, and we also make the edge from W directly to some triangle. From this to some triangle. This is just 1 edge, because it's too
And
long.
here are adjacent triangles.
Yeah, not necessary to be adjacent. Just to find arbitrary 2. Not arbitrary, you can find 2. Yeah.
Are the W vertices adjacent?
Yeah, we can select to be adjacent. Okay, it is adjacent.
Then the cycle is easy, right?
Sorry?
Then for the new cycle, can't you just go from X to one of the W's and go to the old cycle zigzag way and come to the second W and back?
Right.
Yes.
But to make everything as a rainbow, maybe to be
But-
careful.
I thought every edge still has distinct color. No?
Initially.
But
Yeah, I think the new 4 edges also you said you would add distinct color.
Yes. Right. So it's not clear whether we need why we need the edges from the top of the triangles to.
Yeah.
So in your picture, do you want the bottom path to be the same length as the number of teeth?
The teeth, yes, actually we will use a very expensive way to do that. So we need the numbers of teeth and the numbers of edges. They can be the same number.
Okay.
Yeah.
Why
But the
is it-
problem in here is if the new color X and XW maybe repeated already appeared in the original structure can be made as a color. So that's why we need additional edges.
Yeah. Oh no, sorry. Like the picture is wrong. Sorry. Yeah, because. Sorry, I'm a little nervous today. So how can we load it? So we find two vertex. W1 and first and this one, and you go come back. Let me see, does it work? Yeah, sorry. No, it's correct. Okay, so no, it's correct. Yeah. Yes. So cool. So how should we find the cycle? Let me follow the check. Follow my chalk. So we should start from B1. Go from here. And directly go to A1, go back to this, and go back to here, and go back to here, and then, yes. Then this. Yes. Yeah, I think it's correct this time. Okay. Yeah, sorry, actually I drew a wrong picture in the papers. No, it's not submitted. So I just have something confusing. Yeah, I'm very sorry. Okay. Okay, now it's correct, right? Okay. Okay. Let me see what I'm doing. Okay. Now, that's the point. Okay, we can find the cycle in the a rainbow cycle. Suppose we can make sure every edge in the graph has distinct colors, then we can find a new rainbow cycle in the whole graph. Correct? Okay. So the next point is like how can we construct the cycle? Because we need to make sure several things. First, every edge before we observe this vertex, every edge has distinct color. The second thing is like what I just say. Given an arbitrary vertex outside, we fix two edges. Then we need to find one teeth in my T set, such that in their common neighbor we can actually there is a teeth in the common neighbors of the given W and the given vertex X, and also do the same thing for W prime and X. I mean, find the teeth above and then connect them. So that's the point. This is a thing we need to make sure it works. Okay, so here actually we use a random method. Yes, actually. So the idea comes from the ideas was first introduced by Alonsokov and Poklowski. So we consider the following random graph H. So because our coloring is proper, which means for each vertex, every vertex every other vertex has a distinct color connected to the x. Correct. So we can consider the following random graph, we pick let C be the color set of H of Kn, and okay, it's a P, and choose P greater than 0, smaller than 1, and we let H P be the subgraph Kn be P. Actually, we pick a random color set in the we pick a random P set in the color set, and then we just pick the subgraph, the random subgraph. Sorry, is it clear? So we give the color set, and we pick a random P set of the color set, and we just pick out all of these edges with this color, and then this is the random graph. As I just say, because it's proper coloring, which means for each vertex it has a distinct color edges. Yes. So give a vertex. So for all of these edges has a distinct color. So you can imagine the graph looks very similar like a GMP. Okay. So the property we're going to prove is lemma. So first, okay, for each U, V, W belongs to VKN, VH. Okay, H. Okay, H and H has the same vertex with Kn. VH. Okay, yeah, you go to VKN. We know that first, the numbers of U roughly Pn, and second, NH U intersect NH V. The common neighbors of arbitrarily two vertices, roughly P squared N. And third, NH U intersect NH V intersect NH W, roughly P Q N. Okay, we can prove this use some probabilistic method, like just prove the concentration of this. Now you just believe this. You could believe this true. So actually, we will prove lemma. There exists such observer structure inside H. Once we pick some correct P.
So let me try to recap. So the P is some probability that you chose.
Yeah, I choose.
And then you're gonna select.
I will review the random graph. And
Right,
then,
so you had initially the edge colored graph, properly
Yeah.
edge colored graph,
Yeah.
and with the probability P, you're selecting random subgraph with GMP or
no.
you're
So
selecting
this
random.
is a random graph. We reviewed this random graph in Kn. So it is a fixed H, for arbitrary fixed H. I claim I can not this 4H, not this 4H used to observe the actual vertices, just the observer. I claim we can find the structure in H.
Yeah, I think you're picking a random set of colors, right?
So to each color you choose probability P.
Yeah, each color. Yeah.
Okay.
Yeah,
so
yeah.
that's
Let
what
P
you
be the
mean.
color set, and we choose the P subset of the color.
Oh, I see. So that's the.
So sorry,
Alright,
this is
that's-
confusing.
Okay.
Okay. Yeah.
Mhm.
So does the lemma says that for any p we can find, if n is large, then we can find such structure, or if p is some close number to 1, then we can find such structure. What is
Actually, here we need p to prove this true. We need p greater than some log factor, like log n cube over n or something. Yes, cube or something. But once you select, once the graph H has this property, we can find this structure.
So it means p is not super small, then we can find such structure.
Yeah.
But here you have triangles in the absorber.
Yeah, yeah, we have
Triangles appearing, taking p to be that small is okay. If you take too small p, you don't even have triangles in random subplot.
The p is not too small actually.
Logarithm divided triangles.
Um,
Okay.
no, p is not too small. Like yeah. Okay, so to construct this, so first, suppose we already fix a T set. We already have a T set. A1 to A top. This is the arbitrary T set. Later I will choose a special T set, but here is the arbitrary T set. Now I want to construct an absorber such that A1 to A tau, they are the T's of the structure. So first we arbitrarily pick one vertex in the neighborhood of A1, A2. We can do that because by the first property, the neighborhood of A1 is very large. In H, I mean, everything's in H. And then I pick arbitrary, let me see. So next, we can pick a B2 in the common neighbor of B1, A1, and A2. This is also true because by the third property, we can find a very big common neighbor for 3 vertices. And then for A3, we also do this. And finally, you can get this structure. Sorry, not. You can get structure like this. And with B tau. Yes. And then you find the common neighbor of A tau and B tau by the property 2. B tau plus 1. I mean, every step is greatly to do that, such as I already had distinct colors. And finally, you do it. You start from B tau plus 1 and go back to B1. Still greatly. So by the first property, you can also find a lot of edges in the edge of, yeah. Then you can construct the structure, right?
How big is the tau? Like,
Tau is little o in. Tau is, yeah, let me see. Yeah, tau is little o in. Yeah.
So we have plenty of remaining vertices.
Yeah. Okay. So next thing, like, we already have a.
Should be on the P times
PQ.
Times n.
Yeah. Maybe it depends on the P.
Because when you choose the co-neighbor of triple vertices, you need to avoid previous.
Yeah. Yeah, sure. Yeah, so, yeah, actually in our application, we will choose P to be a small constant. So, yeah. So now we have a rainbow structure. Remember, we want to absorb vertices outside, also rainbowly. Which means for each vertex, we want to find we fix arbitrarily to W and W prime. So we want to find edge in the common, we want to find some T's in my graph such that the T's in my common neighbor of. We want the four edge also have distinct colors. So, which means I don't want. So the difficult thing is like how to make sure these four edges has distinct colors with previous thing, because here we already have a quite big rainbow structure. So the strategy is we just choose these four edges outside of edge. So to make sure we can observe one vertex, which means, okay, remember like I haven't told you how to select the teeth, right? So to select the teeth, we need to make sure we can always find we can always find the common neighbor in X and W and XW prime, such that the edges are not contained in H. So we just randomly pick a set, randomly pick a T set in random pick a T set. It's another randomness. So remember, like we already reviewed H. So now we randomly pick a T set. Such that there exists A, V, K, N, such that for arbitrary smaller or equal than some 4, some little Pn. Yeah. So how to make sure the set of A exists? We just randomly pick a set inside the inside the vertices of K, and then it's fine. Yeah. I think it's fun. Okay.
How do you absorb more than one vertex? Are you gonna do this often?
So, first, okay, given the structure here, okay, here's the structure. Suppose we have x1, x2, and xm. So for the first x1, let's pick w1 and w2. There's a fix. So we find one t set, one t vertex in the common neighbor of w1 and x1. Okay, maybe a2. And also a common neighbor w2 and x1. Sorry. Yes. And then and then it's okay. We don't consider the selected A2 and A3 in the T set. And for the second X2, we consider W2 and W3, maybe W3 and W4 if it's okay. So also consider the common neighbors of W3 and X2. You can find another 2. And also W4 and X2 to find another tooth vertex. And do it greatly. Yeah. Because in summary, we just need to observe natural Newton log vertices. Suppose the structure is some epsilon times n, and the choice are all epsilon times n, and you can greatly to observe all the vertices. Okay.
How do you assure at the beginning all the edges in the observer have distinct colors?
At the beginning or the...
So when we find the observer, we wanted all the edges to have distinct colors?
Sorry?
So,
no.
when we first tried to find the rainbow cycle,
Okay.
we needed the structure to have all distinct colors.
Okay. So this is the constructor. This is the lemma. So when we really prove the theorem, so we give a Kn. First, we find the observer. Next, remove all the vertices of the observer outside of Kn. So the remaining graph is still a complete graph and also proper colored. Correct. And then we apply this result in the remaining world because the size is little n. So in the remaining world, you can also get a n minus little n near rainbow cycle. A rainbow near a big cycle. Then you use the outside structure to observe all the vertices. Yeah. Okay. So next I want to share with you some further questions. The first conjecture is this, but I think, the first conjecture is the common color conjecture. So I want to bound the common color of the two cycles, but yeah. So another direction to generalize this result. I think the first conjecture should be very hard. The second question is, what if we consider about the power of cycle? So a two power of a cycle, which means first you have a cycle, and then you connected every pair of vertices with length 2. With with distance 2. Okay, this is the square of the cycle, and in general you can consider the general power of cycle. So because a powers of cycle had a powers of cycle CK2, it has k vertices and 2k edges, right? So in Kn, we cannot expect to find rainbow square of cycle with length beyond n over 2. Yeah, because it has n over 2 times 2 edges. Yeah, because we talked previously, there is a proper coloring, use just n minus 1 colors. So you may be able to find 2 with so conjecture in Kn. So the point, like instead of yes, conjecture we want to find given r greater or equal than 2. So we want to find r plus 1 rainbow copy of r power of cycles partition Vkn. So because when r equal to 1 is what we prove, you can find 2 rainbow cycles partitioning two rainbow powers of cycles. These cycles may not have the same size. Yeah, as we prove, one big and one small. And yes, do you have any question about this? Okay, first for R powers of cycle, it is fine.
But in here, we do not assume the overlapping colors between each power of cycles, right?
Yes, the common colors, we don't do that. Yeah, so the optimal way maybe to get n over r cycles with size. Yes, so r, this, n minus little o n, the powers of cycles of this size. And finally, you get a small one outside little n to absorb all the remaining vertices. Yeah, so actually, as we see, in our proof, we use this result like a black box. And we use a absorbing method. And actually, it's not how to generalize our absorbing method to this case. The hard part is to prove a generalized result of this result.
Do you know how they include that result?
Yes. So the result, this result actually here. So if you want to find a big rainbow cycle, the first step is you find a big rainbow forest, which means every edge, a big rainbow path forest, such that the numbers of edges, the numbers of paths are not too much, and the whole system are rainbow. That's the first step. Then you just use like the random way, also similar like that, to glue all of them together to a rainbow cycle. So the hard part is to find the rainbow forest here. So in this paper and the Pogrovsky Alon's paper, they use a very elegant way like induction. But I think it seems impossible to generalize to this. Instead, Montgomery Pogrovsky had another paper like 2 years after this. They use a just way of color inverted Rödl-Snibel. So that paper called like a decomposition structure into some random thing. We can talk about later. And I think use the Rödl-Snibel way, we can do that. Let's talk a little bit about Rödl-Snibel. So now what we're doing, we want to find a way to find a very big rainbow forest. So find a big rainbow forest first, like given a bipartite graph, a properly colored bipartite graph. So there exists Montgomery, Pogrovsky, they find a semi-random method to find a rainbow matching, which is almost a perfect matching. So that's the black box. Okay. With that, then you can find a lot of, you can find a partition of the whole world and find a matching, and find a matching, find a matching. So because everything are rainbow, and you can find a very big rainbow forest. And I think this is a possible method to generalize to find. But we haven't thought about it clearly. I think it's possible to use this method to generalize this.
What is the approach used by Alon Swarko
Which one?
N to the power of 3/4.
This?
Yes.
They also use the similar way to. They also find a big rainbow forest first. The only difference is like they use a previous way to glue them to a cycle, but they waste too much. And later, usually they use a more clever way to glue the passes more efficiently, like the waste less, and to optimize this result. So the only thing is like how to glue this thing. But for our case, we need to first find a substitution of the rainbow forest, right? Because if we want the R's powers of cycles, first we need to find a generalized. How to draw it. That's the first question, right? And then let's think about how to glue them together. That's the second question. But I think it's possible because we can find a matching first, right? We have the base done, basic done.
Any more questions?
I have one question in your proof. Maybe I'm confusing now. So in here, in your first step to constructing the attributes, you randomly choose some nice color sets first. And then in the random graph, which is induced by those colors, you can find maybe as observers.
Okay.
And then after that, you will apply this log and bolus result as a black box, right?
Yeah.
But in here, you removed all the key, maybe some size of the color sets.
Okay.
Then in here, the remaining thing is still not that does not complete graph. So we cannot directly apply that theorem as a black box.
Apply this like black box to prove what?
Yeah, I mean, if you remove some color class
Okay.
in the first complete graph,
Okay.
then the outside of the vertices, those vertices, the outside of that, the observer,
Okay.
and
Ah.
the remaining thing is not a complete graph. So you cannot apply that on a black box, okay?
Sorry, more slowly.
So just assume that you remove all the red edges. You choose all the red edges in your first step.
Okay.
Then just assume that you find that kind of very nice rainbow observer
Okay.
in this red and blue edges.
Okay.
Then the remaining graph, you don't have a red and blue edges, so you cannot apply this color.
Actually, but you already proved something stronger. Actually, not a little bit. Actually, you already proved. Instead of kn, they can prove if the minimal degree, yes,
Then it makes
greater or equal than some 1 minus delta times n. This does not necessarily to be constant. It could be something like, I don't remember, but a little n. Yeah. Then you can find cycles actually with n minus some large constant, 124 something. I did a calculation times the delta n. So as Helmut just said, maybe you can improve this into little delta n. Then you're almost successful, right? But the point, we cannot control the color outside of the structure, right? Yeah, but I think to do that, I'm not surprised if some people use a random way to absorbing the vertices. Because look, in our construction, we use a very rough, greedy way to generalize the whole structure. So maybe you can randomize to construct the construction and use a random way to absorbing the vertices, such that you can, when you absorb your vertices, you can just use the color inside the edge to do that. And then we need to improve this result. But I think it should be very hard. Yeah.
Right. Any more questions? We lost the opportunity to thank the speaker before asking questions. Anyway, all right, let's thank the speaker.